Assalamualaikum and good day to students of MECR0013 Cryptography. We will continue today with Chapter 5, Introduction to Modern Symmetric Key Ciphers. Previously in Chapter 3, we have looked at the traditional kind of symmetric key, transposition, substitution, what was used in the old days, but now, look at the modern one like AES, for example. We will look at AES later, but before that, in Chapter 5, we are going to first learn about what are the components that made up the modern symmetric key ciphers. So let's begin Chapter 5. So we're gonna try. Not we're gonna try, but we will distinguish between traditional and modern. Traditional is more on substitution, transposition. They are also in modern, but with more components. So then later on, we're going to look at the modern block cipher. First block, because majority of the technique here that we are going to learn are modern block cipher. And then we're going to see why, between substitution and transposition, why modern block cipher need to be designed as substitution. Substitution must be there. If it's transposition, you will see that it's not as secure. It's easily crackable. And then after that, we look at the components of block cipher: P-box, S-box, swap, XOR, and a few more. So after we're done with the block cipher, we look at the stream cipher and distinguish between synchronous and non-synchronous. And finally, we look at feedback shift register for implementing stream cipher. So let's begin. So a symmetric key modern block cipher encrypts n bit block of plain text. So we are going to, if we wrote a long email, like 300, is 300 words long? Let's say 300 words, of an email. So we are not going to encrypt a character by character or a bit by bit. We are going to split the 300 words. Maybe better way of giving an example is 300 characters. Better that way. Every character is specific 8 bits, isn't it? If I say 300 words, one word might be 2 letter off, 2, another word might be 5 character dream, and so on. So we have 300 characters email that you sent. All right, so we are going to break it into different specific block, block by block. So each block might be 5 characters. So we are going to encrypt using the same technique, block 1, block 2, block 3, and so on. And similarly, when we decrypt, we are going to decrypt n-bit block of ciphertext. And both of it are using the same key, and also the key also has a specific size of bit, specific size of key. All right, so we're going to discuss first, remember from Chapter 3, substitution and transposition. So let's look at that first. What are they in modern type? So in modern block cipher, the difference is that we have substitution and transposition. So of course, we're doing it in block. So n-bit plain text, put it inside here. So the encryption technique would be here. Maybe in the old, you use an old one like dash, triple dash, AES, and other technique. And then it will produce same size and bit ciphertext. So the encryption will be using k-bit key. So it can be 64-bit key, 128-bit keys, and the same ciphertext, you will do it backwards. We call it decryption using the same technique. using the same key to get back the original plain text of same size. So that is modern block cipher. So if you remember in chapter 3, when we have one of the example of the transposition where we split it into 5 characters, but the last character has only 4, the last block has only 4 characters. Remember, and we have to put in a filler with the letter Z, Z, yeah? So that Z, we call it padding, yeah? Padding. So, all right, same thing we apply when we are doing in a block. Each block, you must put it, all the blocks must have the same amount of bits. This is like, okay, when we buy a pre-packaged a box, right? So you have to fill it in. So remember, we put in newspaper or styrofoam, those things, so that it's packed, right? So same thing. So in a case of, okay, let's try. How many padding bits are needed? All right. So this is a little bit of mathematics. Just we want to lay down the foundation of the blocks first before we look at the technique. So first, the question asks, how many padding bits must be added? So the padding bits can be 1 or 0 because now we are specifically saying bits, yeah? Bits, not characters. So how many padding bits must be added to a message of 100 characters? Okay, so you wrote an email of 100 characters. So each characters is 8 bit. Yeah, we are using 8-bit ASCII. So 100 characters, and each character is 8 bits. So how many total bits? So 100 character times 8 bits per character, right? Every character, so 8 bits per character. Every character is 8 bits. So we cancel character. We cancel character. So we get 800 bits. Yeah. So 100 characters equals to 800 bits. One character 8 bits. 800 character. One character 8 bits. 100 character 800 bits. So we have 800 bits. Can you imagine? 800 bits. Each block that we want to separate these 800 bits into different blocks into a box, and the size of each block is 64 bit. Okay, the size is 64 bits. So how many blocks can we have? So the easiest way to do is 800 divided by 64. So what is 800 divided by 64? Where's my calculator? In my at my office. Okay, never mind. We can 800 divided by 64. Let's find our calculator here. Okay. Hello, calculator, where are you? Okay. 800 divided by 64. Okay, you get 12.5. Yeah, you get 12.5, meaning there are 12 full, you get 12.5, isn't it? So the answer is 12.5. So 12 full blocks of 64 bits. Yeah. So 12 times 64. And there's one block with only 32 bits. Okay. So total is, this is 12 times 64 is 768, right? Plus 32 yeah, you get the answer is 800 bits. So in total, you will need 13 blocks. You will need 13 blocks, but the last block is only 32 bit. It's not full. It is only half full, isn't it? The last block, the 13th block, the last block is only half full. So how can we make the last block full also? So we have to add something there. So we add the padding bits, yeah, until it is fitted, yeah, with 64 bits. So how many? If we have 32 now, how many we must add to get 64? Yeah, so 64 minus 32. So the padding bits is 32 bits. Yeah, this is the layman term of me helping you understand this in terms of basic mathematics. So if you have 800 bits, you want to put it in different block. Each block is 64 bit. You will end up with 12 blocks of full 64 bit, but you have extra 32 bits that you put in the last block, but you can't have half full block. You must make sure that it is full also. So what you can do is you add in padding bit. Yeah, then only you can apply it to your AES, your symmetric key cipher, because all the techniques will rely on a specific number of plain text. So if that technique asks for 64-bit plain text and you only give it 32 bits, the technique won't work. So that's why we put in padding bits. Okay. However, with small size like 800 bits and 64 bits of size, yeah, block size, you can do basic math like this. But when we have large number of, yeah, big, very big block and very big message, it's quite troublesome to do this math. So we do have a formula. We do have a formula. So the formula says the message, okay, can you imagine? So we have full message, M1, M2, all these are 64 bit, right? But M2, but the last bit, the 13th block, M13, is only 25 bits. Yeah, it's only 25 bit. Sorry, it's only 32 bits. Okay. So what you need to do is you must add padding here. So message plus padding must equal 64. Right? Must equal 64. Look, message plus padding must equal 64. But we are talking about modulus. All our calculation in cryptography, majority, 90% will be on modulus. So in modulus calculation, what this means is that there is no zero here. Meaning, when you divide by 64, you don't get any balance. Or what do you call it, modulus balance is remainder. You don't get any remainder. Okay? For example, the last bit is 32. Yeah? And the padding, we agree, is also 32. So 32 plus 32 is 64. All right? And 64 mod 64 is what? 64 mod 64 is 0. Meaning, sorry, it is, there is no balance. There is no remainder. Yeah, it is 0. 64 mod 64. 64 minus 64, there's no balance. So that is correct. Yeah, okay. So, this is because I already know. We already did the calculation of 32 here, isn't it? We already did the calculation 32. If we use the original calculation, the original formula, yeah. All right. So let me add a new here and let me insert the text box. Okay. The formula says M plus, yeah, this is absolute value, yeah, M plus E. You just uh, understand what this formula means. You don't have to memorize, yeah, but you know what it's used for. M plus B, M plus P must have no remainder when we divide by 64. Okay, so we know that our message in the last block just now, our message is what's left? 12 blocks, full 64. The last block has only 32. So we know that 32-bit our message, but we don't know the padding, right? This is what we want to find. Okay, we want to know how big is the padding. Okay, so 0 mode 64. So far, yeah. So we know the message 32. We plug in P. So basic mathematics. So P is 0 minus oh, okay. Sorry. Our total message. I got distracted because here I already show you here I already show you how to get the last block kan immediately without using the formula. Okay, when we use the formula, we must think of the whole message. So it's good you know the difference. Yeah. So our top original message is 800 bits. All right. So we want to know how many bits of padding that we need. So our message here is 800 bit total. Okay. So P is 0 minus 800. All right. Let me do it long way. Modulus 64. And P, I'll drop the absolute, is minus 800 mod 64. Okay. So what you can do is, yeah, this is quite a big number. Okay. So you can keep on adding 64 until you get the first positive number. So 8 minus 800 plus 64, still negative. Plus 64, still negative. Plus 64, still negative. Until you get the first positive number. Okay, and then you will end up with 32 mod 64. Same way. So this means that with 800 bits of original message, yeah, you will get many blocks. In this formula, it won't tell you how many blocks. It only will tell you how many padding bits with this formula. So we know that we will have a few full block of 64-bit, but our last bit will need 32 bits padding. So with this formula, we use the total number of bits in the whole message to find out how many bits. But in this one, above, yeah, when I divide by 64, the total bit 800 divided by 64, I can know how many blocks we use. We will use 12.5, 13 blocks. 12 full blocks. The last block needs padding. How many? 32 bits. So now we have established full blocks. So we have block, and all the blocks are full. Then only we can plug in our AES encryption. Okay, put in the plain text 64-bit and then run our encryption technique. If AES needs 64, for example, but you only give 32 because the last block is 32-bit, it won't work. Your technique won't work. You must give, if they need 64-bit, you must give the plain text. Yeah, you must give plain text of 64 bits. That's why we must add padding bits. All right? Okay. So, a modern block cipher, okay, so we have established our block size. So now, a modern block cipher, yeah, can be designed to act as a substitution cipher or a transposition cipher. Up to you. Or you can combine. But now we are talking about substitution versus transposition. Your cipher, your modern cipher, can be substitution. A becomes Z, B becomes Y, C becomes X, and so on. Or it can be a transposition cipher. You rearrange the position. Yeah. However, let's look at this note. To be resistant to exhaustive search attack, a modern block cipher actually, even though it says you can make it substitution or you can make it as a transposition, but to be resistant to exhaustive search attack, a modern block cipher needs to be designed as a substitution. Okay? It cannot be transposition alone. You can combine substitution transposition, or you can make it substitution alone. You cannot, so it has to have a substitution component. Huh? Why? 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 Why do you think? Okay, let's think this way. Transposition, why is not a good idea to, substitution is better in terms of exhaustive search attack. Exhaustive search attack means like brute force. They try every combination, okay? Because, okay, the answer is here. Let's give you a specific example. Suppose that we have a block cipher, okay, where n is 64, okay? So if there are 10 ones, yeah, 10 ones in the cipher text, how many trial and error, exhaustive search, brute force, how many trial and error, they keep trying every combination, does if need to do to recover the plain text from the intercepted cipher text in each of these following cases? First, yeah, what if this cipher is designed as a substitution cipher? Okay. How about transposition? Okay. I'll show you the answer to transposition first. Then you'll see why substitution is better. B, yeah. In the second case, if knows that there are exactly 10 ones. Because remember, in transposition, you don't change the character. You don't substitute. Yeah, you don't substitute. Sorry, you don't substitute the character. If it is, for example, roses, okay. In transposition, you might change it to become SRESO. So still, in the original plain text, there's 2 S's. In your cipher text also, after transposition, there is still 2 S's. Then you can just play around. Okay, what if the first one is S? And what is the second one? You try every combination there is. All right. So if can launch an exhaustive search attack using only, if this is 5 bits, 5 characters, much easier. Yeah, even 64-bit block. Try, because if already know there are 10 ones, exactly, we have 10. So you don't try and error 11 ones or 9 ones, 10. So you can try, you can eventually exhaustive, yeah, you can find the answer. That's why transposition not that you can't stop exhaustive search that well. Yeah. But in substitution, you have to guess first. What does A becomes? Is B equals to Z? So many different permutation if we use substitution. Because if has no idea how many ones, because maybe S becomes Y. Yeah? And then maybe the second layer S becomes something else. Okay? Even so, if needs to try all possible 2 to the power of 64-bit block to find one that makes sense. Okay? So that is why in exhaustive search, much easier or much better, we use substitution technique, substitution cipher. Okay? Substitution component. Don't use transposition. Transposition, you can guess how many because you are just rearranging the name. So if as an intruder can also rearrange. Try this one. Okay, no, doesn't make sense. What is this? What is this name? Okay, try again another one. Okay, this one looks familiar. This one looks like a human name. Yeah, so they can try for transposition. But for substitution, not as easy. It takes longer time. So that's why substitution is better for exhaustive search attack. All right. Got it? Okay, good. So, all right. Let me see. So before we go into this, all right, let me stop here for the first part and then we continue second part with this slide.